In Lecture 9b, we will use a one-sample t-test and a t-distribution to decide if a sample mean came up from a population with a hypothesized mean and write an interpretation. We will also decide if a sample R came from a population in which the correlation between the two variables is 0 and write an interpretation of that test. Finally, we will explain what rejecting the null hypothesis means and what retaining the null hypothesis means.
In this first example, we are going to calculate a t-test statistic and determine whether we have enough evidence to reject a null hypothesis in favor of an alternate. So the scenario here is that there are 6 observations, and the sum of those observations was 30, and the sum of the squared observations was 180. And we need that information because the first thing we have to do is we have to calculate the value of the standard error of the mean. Now the standard error of the mean is S sub x bar, and you need to calculate that using S hat for the predicted standard deviation over the square root of n, sample size. So n I know is 6, but S hat I don't have. I do have the information I need to find it though. So S hat from several chapters ago is found by taking the sum of these squared values and subtracting the quotient of the sum of the values, quantity squared divided by n, all over n minus 1. This minus 1, remember, is what makes this a predicted standard deviation and not an actual standard deviation. So now I'm going to just plug and chug in my values. So I have S hat is equal to the square root of 180 minus 30 quantity squared over 6 all over 6 minus 1. If you work that out, you get the square root of 180 over minus 150 all over 5. The top becomes 30. 30 divided by 5 is 6. So S hat is the square root of 6. I'm going to go ahead and add that to my list here. Top. You can go ahead and work that square root out, and it comes out to be 2.4495. Now that's not the value of S that I need though. Remember, I need S sub x bar because I've taken a sample mean, so I need to still take that S hat and apply it to the S sub x bar formula. And I do that by simply taking S hat, which I'm going to write as root 6, and you'll see why here in a second, over the square root of n, which is also 6. So square root of 6 divided by square root of 6 gives me 1. How convenient. Alright, so I now have the answer to number 1, which is the S sub x bar is a value of 1. The next thing it asks me to do is to compare the value for the mean to a certain null hypothesis. Now, in this case, the null hypothesis has been given as the population mean is equal to 3, and then I have a non-directional two-way alternate hypothesis, just saying that the mean is not equal to 3. So to calculate the t value, I need t is equal to the value of interest, in this case x bar, minus the mu that we're claiming it to, all over the S sub x bar. So x bar, if I know the sum was 30 and there were 6 observations, that means the mean was 5. I'm going to take 5 minus 3, and the 3 comes from the null hypothesis. Divide that by 1, which is our S sub x bar, and obviously we get an answer of 2. Now this right here is the value of my t-test statistic. So that is the answer to this first bullet in question 2. Now what do we do with that? That's what's new here today, is that we are now going to take that value and make a decision about the null hypothesis by comparing it to the critical value for this particular set of degrees of freedom and level of alpha. So since my n was 6, n minus 1 is the degrees of freedom, so I have 5 degrees of freedom. So I'm looking at this row here, and I'm going to test first the 95% confidence level, which corresponds to a two-way alpha of 0.05. So the way you write this for the T critical, it's a T at 0.05 parentheses DF equals 5. That tells me this is the critical value for T at 5 degrees of freedom for an alpha of 0.05. And if I look really closely at that, it looks like it's 2.571, which means that in my drawing up here, which I've actually gone out and found a T distribution for this particular degrees of freedom, at 2.5 on either side is going to mark the regions, remember that we call the rejection regions. If my value that I calculated for the T test statistic, which was, where did it go? I must have erased it. It was 2. That's right. It's 2. T equals 2. If that value is in the rejection region, then we can reject the null. If it's not, we fail to reject the null. So here's my T value of 2, either plus or minus, it doesn't matter. It's a two-tailed test. And you can see that I have not managed to meet or exceed the critical values. So my conclusion for an alpha of 0.05 is that I would fail to reject the null hypothesis in favor of an alternate. And remember, Spatz also says retain the null as an option. If I can't reject it at 0.05, I'm certainly not going to be able to reject it at a more stringent level of alpha. So I'm not even going to bother looking at that. The conclusion being fail to reject at all levels of alpha, 0.05, 0.01, and 0.001.
Okay, I also want to use the same set of data to test a one-tailed hypothesis. And unfortunately, I just noticed that I've got a bit of a typo here. This greater than sign should be a less than sign in the alternate. So the true alternate hypothesis for this next problem is going to be mu sub 0 is less than 8. Sorry about that. Okay, so the good news though is that my S sub x bar is still the same. It was 1. And my mean is still the same, because the mean, remember, came from taking the sum of the scores divided by the n. Okay, so the question is my actual mean this time of 5 significantly less than this hypothesized mean of 8? And less than is what makes it the one-tailed alternate hypothesis. So my t-test statistic, the only thing that's going to change here is the value for what I'm comparing it to, because that always comes from your null and alternate hypothesis, the value there. So it's still 5, that's still my mean, but now I'm going to subtract 8 from it, and I'm still dividing by S sub x bar of 1. I very quickly see that I have a -3 for my t-test statistic. Now, I need to be a little bit wary here because it is directional. I don't want to look at the alpha for a two-tailed. I want to only look at the alpha for a one-tailed. I still have 5 degrees of freedom because remember n was 6. And now here is my column for 0.05. And I see that my t-test critical value is going to be 2.015. So I'm going to go to where that is, to about negative 2.015. And I'm going negative just because everything here is negative and I'm looking for less than. Okay. And I can see that, yes, indeed, my value of 3, -3, is well within the rejection range. So I can say with confidence, 95% confidence actually, we'll get to, but at alpha of 0.05, there is enough evidence to reject the null hypothesis in favor of the alternate hypothesis, meaning there is likely a significant significantly lower mean than hypothesized. All right, my handwriting is horrible with the stylus, but I said it, so you should be able to figure it out from there. Will it be significant at more stringent levels? I'm not sure. We need to check. And by checking, that means we need to look for the 0.01, and the 0.001 isn't here. So let's test 0.01, because if that's significant, then we have to worry about going further. But if it's not, we don't, and it's not. So the critical value for 5 degrees of freedom at alpha of 0.01 for a one-tailed test is 3.365. So that would mean that my rejection region is still out of reach for my t-test statistic of -3. So I don't need to worry about the fact that 0.001 isn't on this table. And in fact, if you get a significance at the 99% confidence level or the 0.01 alpha, you're feeling pretty good about yourself. So you really generally won't look for that 99.9th percentile value. So not only can I state that it is significant at the alpha of 0.05, I can state that it is not significant at 0.01. Okay, so while I'm willing to accept a 5% chance that I could be wrong, I can't accept a 1% chance, is basically what that boils down to. And we'll delve into that in more detail with the type 1 and type 2 errors when we get into lecture 9C.
Okay, in the second example, I now actually have a context for it. The psychologist who taught the introductory psychology course always gave her class a misinformation test on the first day of class. Her test contained some commonly held incorrect beliefs about psychology. Over the years, the mean number of errors on this test has been 21.50. The data for this year follow, and we want to analyze these data with a t-test. And then later, we'll actually do the rest of this, which is calculate the effect size and write the conclusion that go with it. So let's start off with figuring out what our hypotheses are. The null hypothesis is always a statement of no effect. So the mean is going to be equal to what it always is. Basically, the question is, are her students this semester any different than students in past semesters? That's really what she's asking. The alternate hypothesis, because it doesn't really specify the idea that she thinks these students are more informed or less informed, all we're going to do is we're going to do a two-tailed hypothesis of no difference, and do mu is not equal to 21.50 as our alternate hypothesis. Okay, so same game as last time. I've been given enough information here that I can calculate the S sub x bar, which I'll then use in a t-test. So S hat is what I need first, and remember that is going to be taking the sum of the squared values, in this case 4700, and subtracting the sum of the values, quantity squared, divided by n, which is 11, and then on the bottom it's n minus 1, so 11 minus 1. That will give me an S hat, if I work out math there, of 4700 minus 3564, all divided by 10. And keep working through the inside of this. I get the square root of 113.6, which leaves me with an S sub hat of 10.6583. Now, S sub hat isn't what I actually need, though. I need S sub x bar. And S sub x bar is the S sub hat divided by the square root of n. So I'm going to take this S sub bar and calculate it by taking 10.6583 divided by the square root of n, not n minus 1, that's a mistake people make sometimes. So divided by the square root of 11, and I get an S sub x bar of 3.2136, and that's the value I actually care about. So I'm going to give myself some space here and focus on just the value that I care about, which is the S sub x bar. So S sub x bar is equal to 3.2136. Now, to calculate the t-test, I'll need the mean for this particular set of scores. I know the sum of the scores was 198, and there were 11 scores, which gives me a mean of 18. So is 18, this class's mean, significantly different than the historic mean for all of her previous classes of 21.5? That's the question we're trying to answer. So t is going to be the value of interest, 18, minus the comparison value, 21.5, divided by the standard error of the mean, 3.2136. That gives me a value of negative 1.09. This is my t-test statistic. Now that I know my t-test statistic, all I need to do is look at the t-distribution and figure out where my rejection region is. And to do that, I need to look at table B, and degrees of freedom are n-1, so I'm looking at row for DF 10. And I would like for a 95% confidence level. And I see that my value for T sub alpha is 2.228. I'm pretty sure that's what that says. 2.228. And so 2.228 is what I would call my T sub 0.05 parentheses DF equals 10. That's my critical values. So that would mark my rejection regions. And in this case, I fail to meet or exceed that rejection region because I'm stuck way back here at 1.09-ish. So the conclusion would fail to reject the null hypothesis, meaning that her students this semester, even though their mean was lower, it was an 18, it was lower than the historical mean of 21.5. It wasn't low enough to be called statistically significant. So it could have just been a chance sample alone, and not that these students are any more well-informed than previous students were because they had less errors. All right, in this example, the data are from an old study, 1984, where the authors looked at 6-month-old infants who had low birth weights. Each child was measured using a particular development index, the BPDI. The population mean has been set at 100, and high scores generally mean better performance on the psychomotor development index. So we want to perform a t-test. Same game as always. We want to start off with a null hypothesis, statement of no effect or no difference. So we suspect that in the population, these 6-month-old infants who are low birth weight will score no differently on the BPDI, meaning they'll have the same mean of 100. And alternate, the authors don't really specify what they think the child or children's average will be. They say something about high scores meaning better, but they don't actually say they think they're going to perform better. So I'm going to stick to a two-tailed alternate hypothesis where it's just a non-directional, where the mu is not equal to 100. So those will be the hypotheses we test. In order to do that, to calculate the t-test statistic, we'll need that value of S sub x bar. So that's our first goal, is to find that value. So what I'm going to do is I'm going to begin by getting the squared values of my x's. And I worked these ahead of time on my calculator, so it's going fairly quickly. If you'd like to confirm them, you certainly may. But all I did was take, like this one is 110 times 110, which gives me 121.00. And 99 squared is 9801. 112 squared is 125.44. 103 is 106.09. Here's another 99. Same value. And 11881. 11449. and 10816. Of course, if you want to use Excel, you certainly may. Excel can do all of this very easily for you, and you should have enough background knowledge to be able to do that. The sum of the values of x add up to 1041, and the sum of the squared x values is 108621. Those values become important because I need both the mean and the S hat. The mean, since there are 10 scores, I'm just going to take my sum of the x values and divide by 10, and I get 104.1 as the mean. Now, to find S sub x bar, I need S hat. And S hat is calculated by taking the sum of the x squareds and subtracting the quotient when you take the sum of the x values quantity squared divided by n, all divided by n minus 1. So plugging in the values for these, I get S hat is equal to 108621 minus 1041 squared over 10 all over 9. Break that down, and you end up with 252.9 divided by 9, which will give us the square root of 28.1. So S hat equals 5.3009. Not done yet, though. We've got to take that S hat and turn it into an S sub x bar by dividing by the square root of n. So here's my S hat, 5.3009 divided by the square root of 10 gives me an S sub x bar of 1.6763. All right, now t-test statistic time. For the t-test statistic, I'm going to take my value of interest minus the population mean to which I'm comparing it, divided by the standard error of means. So my value of interest was the mean for these babies, so 104.1. Subtract the mean in the hypothesis that we're comparing, all divided by the S sub x bar, which was 1.6763. Gives us a t-test statistic of 2.445. So that's pretty far out on a normal distribution. So I'm suspecting we're going to see a significant difference here. But I don't want to just guess. I want to actually confirm. So for this, I need critical value for t. Let's take an alpha of 0.05, and it's going to be 9 degrees of freedom because it's n minus 1. Critical value of t for a two-tailed 0.05 degrees of freedom of 9 is 2.262. So in my distribution, to mark my rejection regions, I would go 2.262 from the mean, and the rejection regions are anything to the right of that. Take your calculated t-test statistic, and it's 2.4. So reminder, this was 2.262, and my t-test does exceed that. So it would be in the rejection region. So yes, I can reject the null hypothesis. And what that means is that the babies in this particular study, this sample, were on average different than the population mean. Right? I know that it says that it's greater, but we only chose a non-directional hypothesis. So the only thing you can say in your conclusion is that they are different, significantly different, so that this value of 104.1 was not likely to be obtained just due to chance alone. It's likely an actual difference in those particular babies on average. All right, in the next example, we're working with the Rathis Assertiveness Schedule. It's a 30-item questionnaire, and I actually looked it up just to make sure I knew what it was, because it seemed to me weird that some of the scores were negative and some of them were really high and positive. Well, it turns out they could answer on this scale anywhere from a -3 to a +3, with 0 being a neutral statement. So in reality, the lowest score, if somebody answered -3 on every single item, would be a -90, and the highest score would be a 90. So that puts these scores in perspective a little bit more. And the other thing is, when I did find it online, and I just searched for it, and it came right up the full scale, so it's kind of interesting. I did see that the median value, which is the 50th percentile, and if it's normally distributed, also makes it the mean value, was 8 for women. So the background on this particular question from Spatz checks out. So anyhow, what happened was the mean score for women in general in the population is 8. Right? But what's gone on is that there's been an assertiveness, I think I'm saying that right, assertiveness class. And it's a 6-week course, and at the end of the course, they had the 10 women who took it take that scheduled 30-item questionnaire again. And here are their scores. So what we're going to do is we're going to calculate the t-test statistic to see if their scores are different than the national mean. So to start off with, let's get our null hypothesis. Null hypothesis, remember, is always a statement of no effect. So H sub 0 is mu is no different than the population mean, which is 8. The alternate, in this case, there is a direction implied, because if it's a course that's designed to teach these women to be more assertive, then we would expect the mean for this particular group to be greater than 8, which makes this a one-tailed alternate hypothesis. And that'll matter because now, instead of using the alpha level for the two-tailed significance test, we want to focus on the one-tailed. So to calculate this t-test statistic, we need the value of interest minus the comparison mean over the standard deviation of sample means. Now we have the comparison mean, that's 8, and we can find the mean score for this particular sample pretty easily. All we do is add up the x's and divide by how many there are. If you add them up, you end up discovering a total of 220. I worked this ahead of time, so my math will go a little bit faster than it would for you, so feel free to pause. And because there are 10 scores, my x bar then is 220 divided by 10. The 10 cancels, leaving me a mean of 22. So that's a pretty big difference. And so I'm suspecting that I'm going to end up with some sort of a significant difference here. But I don't want to just assume. I want to actually do the math. So let's take each of the values and square it so that we can calculate the S hat value, which we will then use to find the value for S sub x bar. So 20 squared is 400. 36 squared is 1296. 0 squared, that one's easy, 0. 44 squared is 1936. 16 squared is 256. -6 times -6 gives me a positive 36. Remember, anytime you have a negative value and you square it, it gets rid of that negative. 50 times 50 is 2500. 78 times 78 is 784. 24 squared is 576, and 8 squared is 64. Add all those puppies up and you get 7848. Now that we have those values, we can easily calculate the S hat. So S hat, we take by the sum of the squared values, 7848, minus the sum of the values quantity squared, so 220 squared divided by n, n is 10, all over n minus 1, 10 minus 1. Working out the math inside there gives us 3008 divided by 9 in the square root. Keep working it out. Get the square root of 334.22 repeating. And that leads us finally, when we hit the square root button, to an S hat of 18.2817. Now, be wary. I've seen this happen a lot. People start getting excited and they use the S hat in their standard deviation for the t-test statistic. Can't do that because we're working with a sample mean. So we need S sub x bar, which we find from S hat divided by the square root of n. So I'm going to take 18.2817 divided by the square root of 10, and we finally arrive at the value we need for our formula, which is 5.7812. Okay. So t-test statistic, I'm comparing my mean of 22 minus the national mean of 8 all over the standard deviation of sample means, which is 5.7812, and we get a t-test statistic of 2.42. Okay, now to make our conclusion, we need to know what the critical value is for this particular significance level and degrees of freedom. So our DF is n minus 1. There are 10 of them, so I have 9 degrees of freedom. So I'm looking at the 9 degrees of freedom row. And we'll choose an alpha of 0.05. And this is for a one-tailed test. So where these guys intersect is at a t sub 0.05 at df equals 9. The critical value is 1.833. Okay, so if I mark that on my t distribution, 1.833 is going to be somewhere around here. That means that all the regions to the right are rejection regions, which is excellent because my t-test statistic of 2.42 is, and oh, yep, that's right, we only want one side of this, and it was a greater than sign, so I'm only going to look at this side, the right side. And a t-test statistic of 2.42 places me smack in the rejection range, which means that yes, there's enough evidence to reject the null hypothesis, which means that one could state based on the evidence that females who attended this 6-week course in assertiveness do indeed have a larger than normal score on average on this assertiveness schedule, the RAS. Not only can we test the significance of means or other population parameters like, say, standard deviations or variances, we can also look at the significance of a correlation coefficient. If you'll remember, we use the Roman letters for samples and Greek letters for populations. So for means, remember, the sample was x bar and the population was mu. For a correlation, our Roman letter is R for the Pearson product moment correlation. The Greek letter corresponding to that is this funky looking P thing, which actually is rho, R-H-O. So if we're testing a hypothesis for correlation, the idea is that we're curious as to whether there is a correlation or not. If there is, then you'll have some sort of value between negative and positive 1. Remembering that 1.00 is a perfect correlation, so negative 1.00 is as strongly negative as you can get, and positive 1.00 is as strongly positive. Now, for the null hypothesis, therefore, H sub 0, we're testing that oops, wrong symbol. I need rho. We're testing that rho is no different than having no correlation, meaning the correlation would be 0. So this is always your null hypothesis for correlation. The alternate is always going to be one of just difference. Don't worry about one-tailed or two-tailed. They're always a hypothesis of difference because the sign doesn't really tell us anything other than the direction. It doesn't tell us whether a value is greater than 0 or less than 0. It just tells us how strong it is and in which direction. So we don't ever do alternate one-tailed hypotheses for correlations.
So when we're testing the significance of a correlation, again, we're going to calculate a t-test statistic. This time, though, the formula is a little bit different. Spatz has it in a couple of forms, but I like this one the best. It's quite user-friendly. You use the value of the Pearson correlation coefficient, R, where n is the number of pairs of data, x and y, and the degrees of freedom are calculated from those pairs, the number of pairs n minus 2, because there were 2 different sets of data. Again, you'll use a t-distribution for the correct degrees of freedom. Look for a rejection range and see if your t-test statistic is extreme enough to be in that rejection range. So the process is very similar. It's just the math that's a little bit different.
Let's actually do the math to test the significance of some Pearson product moment correlation coefficients. I have 3 set up here of varying strengths, none of them particularly strong. And I have n values. Now n stands for pairs. I want you to remember where these come from. They come from paired XY data. So each pair counts as 1 in the n. I'm going to do one small change here. Let's change this 50 to 100. Just because when I worked it out ahead of time, the 50 wasn't all that interesting, considering we had just done the same thing in number 2. So you'll see why here. Okay, so let's run some numbers. The math is pretty straightforward. I need the R value and the number of pairs. So let's do the first one here. The t-test statistic for an R of 0.49 with 32 pairs of data. Set it up pretty standard. You're good at this by now, all the different mathematical operations. And you end up getting 0.49 times the square root of 28 over 0.7599, which ends at 2.97. And if I look up the critical values for a t of 0.05 alpha at degrees of freedom, remember it's n minus 2 for the degrees of freedom because I have 2 different sets of data. So it's minus 1 for each. So I've got 30 for my degrees of freedom. Look that up on the table and you get 2.042 for your critical value. So if I were to sketch this out, it's a very lumpy t-distribution. Then my critical value is going to be just past the second standard deviation on either side to mark my rejection regions. And my calculated t-test statistic of 2.97 is definitely beyond that, almost to the third standard deviation. So for number 1, I would say that this value of R, 0.49, is statistically significant at alpha equals 0.05. So that would be enough for us to say there is a correlation here, and it's not just that this 0.49 was due to chance. All right, let's do the second one. The only thing that's changing here is my degrees of freedom and my value of R. I'm just going to take those parts out. So now it's a 0.27, and I have 10 pairs. And 10 pairs, 0.27 squared. This results in 0.27 times the square root of 8 over 0.9271, which gives me 0.793. Now my t for an alpha of 0.05 with degrees of freedom of 8, because n was 10 and n minus 2 is my df, gives me a critical value of 2.306. Clearly way farther than my t-test statistic of 0.8-ish. So if I were to draw that out, the rejection regions would be out here in the tails, but my t-test statistic would be somewhere not even to 1 standard deviation away from the mean. So this is an example of fail to reject the null. So even though we have what some books would call a moderate correlation strength, weak to moderate correlation strength, it's actually not statistically significant, which means that it could have been obtained from just chance alone, and we can't actually say it was because a difference or a significant relationship existed. Last one, I just erased the whole thing and I shouldn't have, but oh well. The last one here, what's different is instead of working it for an n of 50, I want to work it for an n of 100, same correlation coefficient as before. So now what's going to change is I've got my third one here, and it's 0.27 still times the square root. Now it's 100 minus 2 all over 1 minus 0.27 quantities squared. So 100 minus 2 is of course 98. 0.27 still there. And 1 minus 0.27 squared is still going to be 0.9271. If I take 98 divided by 0.9271, I get 105.705 blah blah blah. Square root that and times it by 0.27, and I get a t-test statistic of 2.7759. Now I'm very hopeful at this point in time that this is now a statistically significant result. I can confirm that. I'm looking at table D right now. My degrees of freedom are 98, and I'm going to round down just to be on the safe side to 80, and I look for a 5% alpha 0.05 and the degrees of freedom at 80, so T at 0.05 df equals 80, which I realize I could have used 98, but our table doesn't show that specifically, is 1.99. So it really doesn't matter. Even if I went to 100, it wouldn't have mattered because my t-test statistic is now clearly in the rejection region. My critical value of 1.98 would mean that it would cut off right before the second standard deviation. But my t-test statistic is all the way out at 2.77, way far. So this one is now definitely statistically significant. So this is a really good comparison of why researchers try, as Spatz states, to make sure that you get an N of at least 50 pairs of data, because it's really hard to obtain significance with only a few pairs. And partly that's because when you're doing correlations, remember there's all that problems if you have truncated ranges, or if you don't have a complete picture of the data. It's very, very difficult to know if any sort of linear relationship that you're seeing is truly there. It just looks like it's there for that particular set of data. All right, so now you know how to calculate whether a null hypothesis should be rejected or retained for both comparing means and for Pearson product correlation.